Okay, welcome to another screencast. In this one, we're going to cover the infinite sums, and I was just going to explore that kind of idea because what we've looked at so far, if you go back over it, we've been looking at sequences and we've been looking at sequences, which are just an ordered form of numbers that follow some kind of rule. Series, which are the sums of sequences. All right, so these are sums. Both of these are called progressions. Refers to both sequences and series. But when we've looked at sums, we've looked at so series are sums. We've looked at partial sums. So partial sums meaning we've taken parts of a sequence and added them up. What we're going to look at today, I mean, if they're not partial, they're infinite. So we're going to look at infinite sums today, and whether they diverge or converge. Right, that's sort of they're the keywords from this for this screencast. So I'll write down those keywords actually. Converge and diverge. So hopefully there's some understanding of these words. That's no worries. Diverge means going getting bigger or larger without control. There's no constraint. Whereas converge is closing in on something, getting closer to something. If you converge on a meaning or a value, you're getting closer to it. If you're divergent, you're not getting any closer. You're getting further away. So these are our keywords. All right. So the idea of infinite sums. So let's have a little look at perhaps an example. If we just let's say we just pull out just look at a geometric sum and a partial geometric sum like so. Okay. So if we go this far, this here is a partial sum. All right, because it's just part of the sequence. Remember, sequences can be finite or infinite. So this is a finite sequence, so it's a partial sum. Now we can work that sum out. That's 15, and so that we would say converges. The partial sum here is definitely convergent. All right, we'll just make a note of that. That's convergent. Now, if we take this sum and continue, so what are we doing here? We're doubling. Our r is 2, and so off we go. And how do I denote that this is going to go on forever? Just 3 dots. So now this is not a partial sum anymore. This thing here is an infinite sum. An infinite sum, and that certainly does not converge. This is very much a divergent result. So 15, 31, 63, it goes on. It's just going to get larger. It's going to get infinitely large. Okay, so that's one sort of sequence. I want to have a look at another kind of sequence here, and again, geometric, and we are going to concentrate on geometric sequences because infinite sums of arithmetic sequences are not quite as interesting. They're all divergent. What we're going to have a look at here is another geometric sum. So this time, rather than doubling, we're halving. And again, we get to this point here, and that is partial. That's a partial sum. And of course, any partial sum will converge. So that's convergent. Okay, but let's continue. And this is where it gets interesting. We're halving. We're halving. And we're halving forever. Okay, so now this whole sum is an infinite sum. And what's happening? Well, is it divergent or is it convergent? Divergent or convergent? That's the question. Let's have a look at this. So we've got 8, 12, 14, 15, 15 and a half, 15 and 3/4. what's that now? 15 and 7/8, and the next one would be 15 and 15/16, then 15 and 31/32, and then 15 and it looks like it's going to be getting, so if we look at our partial sums, I'll put those, so we're up to here, we're 15. If we just do a partial sum accumulator as we go, 15 and a half here, 15 and 3/4 here. So I'm just adding on the next term, 15 and 7/8 here. If I add a 16th to this, because that's 14/16, the next one will be 15 and 15/16. And you can see what's going on. We're just going to be getting closer. Like that fraction there is getting closer to a whole, but it's not quite getting there. But it's converging on a whole. So this part of our sum is getting closer, it seems, to a whole. So it looks like our partial sum, 8, 12, 14, 15, becoming our infinite sum. This looks like it's heading towards 16. It looks like it's converging on a value. Even though it's an infinite sum, it looks like it's converging. So this is the point of this lesson. When we have a common ratio that is that makes our terms get smaller and smaller and smaller. So think about what value that ratio needs to be in order to make successive terms smaller. Well, if you multiply by anything less than 1, then you are reducing the value of the term. Anything greater, not just less than 1 though, because if you multiply by -2, -5, terms are going to get out of control big. But if it's between -1 and 1 as a common ratio, your terms are going to be getting smaller and smaller and smaller. So what the result of that is that we get a convergent sum. So this is convergent. Okay, convergent when, or why? Why is it convergent? Because, all right, what's different about this sequence here to the first one is that I've gone from a common ratio of 2 to a common ratio of 1/2. These terms are going to get bigger and bigger. These ones are getting smaller and smaller. So it's because r equals 1/2, or more generally, because r is between -1 and 1, not including 0 clearly. When r takes on any value between -1 and 1 except 0, then we have a convergent sum. When it is 0, you're just you've got 0. So it's a trivial example. So when our common ratio is between these values, the geometric sequence or series will converge. All right, and that is really our big take-home message from this screencast. All right, when r is between -1 and 1, the geometric series will converge. Okay, so let's see what these sums are. This looks like it's heading to 16. This one is divergent, we know that. So let's perhaps have a look at what is going on here using what we know about the sum to n terms. So the sum to n terms of a geometric, we know it's u1 by, let's go with the 1 minus r to the n over 1 minus r. Okay, so let's just have a think about this. As n gets larger and larger and larger, think about what is happening. So really, we can't substitute infinity in, but it's a limiting idea. It's a converging idea. As n gets larger and larger, what is happening to this term here? So it's really a focus on r to the power of n. So let's have a look at, so as n approaches infinity, we can certainly talk about n approaching infinity if we can't talk about n equaling infinity. as n approaches infinity, this value r to the power of n, what does its value approach when r is between -1 and 1? Well, we've got a fraction, say a half, that is being raised to larger and larger power. So half squared, a half cubed, we're at a half to the power of 4, a half to the power of 5 is already 1 over 32. So as the power of n gets larger and larger and larger, this value here, with r being between -1 and 1, a fractional value, goes towards 0. So therefore, we write that the infinite sum is equal to u1, 1 minus, now r to the n becomes 0. R to the n becomes 0 when we look at infinitely large sequence of, or an infinitely large sum, over 1 minus r. So what results here? This simplifies down to u1 by 1, so it's just u1 over 1 minus r, and so that there is our infinite sum result. And that's the last of our formulas for this unit of work. We've looked at arithmetic and geometric, the nth term and the sum to n terms. Now we've got an infinite sum for geometric, but we've got to make this is incomplete at the moment. I need to unbox that because we need to add for when r is between -1 and 1. It's not, it's the infinite sum for any other value of r is divergent. And that's perhaps worth taking a note. Okay, so and for these reasons, for the reasons that they are divergent, those sums, they're not considered a terribly fruitful kind of line of inquiry. So, right, start talking about infinite sums. You need to concentrate on your value of r. You need to find. You need to make sure that r is between these values, and then you can go ahead and find the infinite sum. Let's have a look at, well, let's use this sum here as an example. So let's say, e.g., find the infinite sum 8 plus 4 plus 2 plus 1, and on we go. Okay, so what we say here is that, okay, my u1 here, that's equal to 8, that's fine. My r is equal to 4 divided by 8, or 2 divided by 4, or 1 divided by 2, it's a half. And then I think, oh, hang on, I've got a convergent, I do have a convergent infinite sum here. So I can now go and find my infinite sum. It's just u1, which is 8 over 1 minus r, which is just 1 minus a half. 8 over a half, multiplying both top and bottom by 2, I get 16. 16 is my infinite sum. And that's what we figured would be the case here, getting closer and closer to 16. Every partial sum, the denominator doubles, and the numerator is just one less. Right, so how do I write this infinite sum in sigma notation? Let's have a think about that. So it would be from I equals 1 to infinity, because it's in the infinite sum. Now we need to represent this as a this sum in terms of an expression. Now I know that my base has to be a half because my r is a half, but what is my power? So if I just have my index is I, well, that accounts for a half to the power of 1. That accounts for the 1, 2, 3, 4, the fifth term. Okay, and if I can't be adding 1 because that's just making it smaller, so I need to be subtracting to get my first term of 8. I'm actually going to need to, I need to raise, so it's really saying half to the power of what? Half to the power of what is equal to 8. So really this 2, this a half, well, that's 2 to the -1, isn't it? So what do I need to raise that to? This is what a half is, to get 8, which is 2 to the power of 3. Well, this is going to need to be -3, isn't it? So if I need -3 there, then I need I minus my, say, k has to equal -3. So a is equal to, sorry, so not I minus k, but so 1 minus k is going to have to equal -3. So that value of k is going to have to equal 4. So what I'm establishing here is that I need to write a minus 4 up here. This is my sigma notation for this sum. So just checking, I equals 1. You put 1 in here, you get a half to the power of -3. We've just established that a half to the power of -3 is going to give us 8. That gives us our first term, and we're away. Okay, that's just a little aside. Okay, let's do another example. And I want in this example for us to find the, rewrite this. Write 0.74 as a geometric series, and hence find its, or not find its, and hence write as a fraction. So we're converting a recurring decimal to a fraction using by first writing it all via its representation as a geometric series. So as another aside, 0.74, we had a look at these, a question like this in class last term, when we looked at writing it as a fraction by turning it into an algebraic an algebraic problem by letting x equal the decimal that we're concerned with, and allowing it sort of to run 747474, so writing it like so. What we did was, because it's it repeats every 2 decimal places, we wanted to move the decimal place 2 along to the right so that we could pick up the same pattern to the right of the decimal point. And then, if you remember, if we label these as simultaneous equations, then we'd say that 2 minus 1 would give us 99x on the left and 74 on the right, so x would equal 74 over 99. And that's a nice little algebraic maneuver in order to accomplish what we're trying to achieve, and that is to turn 0.74 repeat into a fraction. So what we're going to do now is the same. We want to achieve the same aim. We want to achieve a fraction for this decimal, but we're going to go via a geometric series. So, and it's quite a nice little exercise, this one. So 0.74, we're going to consider this as a geometric series. So let's have a look at it. 74, 74, 74, 74. We get the idea. So if we want to write this now using its place value, we would write this as, think about it, 74 over 100. Right, that accounts for these 2 decimal places here. We would then be looking to add 0.0074, which is 74 over 10,000, to which, so that now accounts for those 4 decimal places, to which we would add 0.000074, which is 74 over, I think, 1 million now, and so on. Okay, this is our sum that we get from this recurring decimal. Okay, but if we have a little closer look at this, we'll notice perhaps that what we're doing each time is we are multiplying by the same common ratio, in this case 1 over 100. We're just adding 2 zeros to the denominator, aren't we? Because we're just shifting across 2 decimal places every time. So we have a geometric series here. Better, because it's a recurring decimal, we have an infinite geometric series, and we have a method by which we can sum this. So here's my u1, and my sum is therefore u1, 74 over 100, over 1 minus r, which is 1 over 100. So this looks like 74 over 1 minus 100, 74 over 99 in my numerator, and 99 over, I'm getting ahead of myself, 74 over 100 here, 99 over 100 in the denominator, which becomes 74 over 99, which we of course expected, but not quite a nice way to achieve that outcome, considering a recurring decimal as an infinite geometric series. Okay, let's have a look at just a couple more examples before I let you go and do some practice with out of exercise 1C. All right, let's have a look at this example, and perhaps you can pause the screen and attempt this. So this example is find the value of okay, we're going to go from I equals 1 to infinity, and we're just going to take 2/3 to the power of I. Okay, so write the first few terms out, get the drift, and then evaluate this infinite sum using what we've just established. Okay, so hopefully you've had a chance to look at this. We put I equals 1 in, and we get 2/3. It's sigma, so we're adding each term as we go. When I equals 2, we've got 2/3 squared. When I equals 3, we've got 2/3 cubed. And this is going on, and I'm not going to put a last term because I don't know it. Okay, so this is 2/3 plus 4/9 plus 8/27, etc. We have a geometric series where 2/3, and I know from here that r is going to equal 2/3, but this verifies it, and u1 is equal to 2/3. 2/3. So my infinite sum, remember, is u1 over 1 minus r. So u1 being 2/3 over 1 minus 2/3, which is 1/3. And if we multiply top and bottom by 3, we get 2. So my infinite sum here is 2. Okay, one more, maybe two more examples. Okay, let's consider this example. We have a series defined by this expression. We can see from the sigma notation that it's an infinite series. And I can see that I've got here 1 plus x over 2. This is my r. R is equal to 1 plus x over 2. So if I put x equals 1 in there, that's 1.5. That's not going to converge. That's going to be a divergent sum. So what we're asked here is for what values of x does this converge? So I need my r to be between -1 and 1. So I need to solve this inequality. Okay, and the way to do that is I'm running two inequalities at once. I'm going to subtract this 1 first from both sides, or all sides of my inequality. So I'm going to subtract 1 here, I'm subtracting 1 in the middle, and I'm subtracting 1 from 1. And lastly, I'll multiply through by 2. So I get this as my result. That means that when x is between -4 and 0, I've got a convergent sum. Now we just need to make sure that we don't consider x equals -2 to be a solution, which is in this range. So we should just say x cannot equal -2, because when x is -2, I've got r equals 0, and that's a nonsense. So that's my solution. Now find the sum when x equals -3 on 2. That's certainly in my limiting sum range, so we can certainly work that out. My sum to infinity. So when x is equal to -3 on 2, I'm going to have, right, let's work this out. I'm going to have r equaling 1 plus -3 on 2 over 2. Okay, let's just tidy this up a bit. Multiply top and bottom by 2. I get this. I get 1 plus -3/4, which is 1/4. So when r is equal to 1/4, so this is my value now of r. So what I'm doing now is I'm evaluating from I equals 1 to infinity of 1/4 to the power of I. Okay, so this is 1/4 plus a 16th plus a 64th. Okay, this is how my sequence looks, my series looks. And so this will be equal to u1 over 1 minus r. So 1/4 over 3/4. 1/4 over 3/4 multiplied by 4, multiplied by 4, 1/3. Okay, last example, a geometric series converges to 8. Okay, so we know that the series is going to 8. So we know this, the infinite sum goes to 8. The second term is -5/2. Find the common ratio. Converges. Okay, so because we're told it converges, it's a series that converges to 8. There's no other type of series that converges other than the ones that have a ratio between -1 and 1. So we know that that's the situation, and this is our information. So given this here, so what I'm suggesting is that there's nowhere in the question does it say infinite. A geometric series converges to 8. The implication there is that we have an infinite number of terms with a common ratio between -1 and 1, and the infinite sum, the convergent sum, is 8. Okay, pause the video and have a go at this question, and then pop back and compare notes. So what this tells me is that u1 over 1 minus r is equal to 8. Okay, what this tells me, that's not enough information to go on. I've got 2 unknowns here. What this tells me is that u1 times r is equal to -5/2. So what I can do is I can use my 2 equations to advantage, and perhaps I will suggest here that u1 from equation 2, u1 is equal to -5/2r, and that can be my equation 3, and then I will perhaps substitute 3 into equation 1, so that I get -5/2r instead of my u1. I've got -5/2r, and I put that over 1 minus r, and that's equal to 8. So working this guy through, I get 8 minus 8r equals -5/2r. Multiplying through by 2r in that step. Gathering everything onto one side in that step. Okay, I'm looking for 2 numbers that do this job for me, and where do I get those numbers from? Multiplies to -80, that comes from -5 times 16, and adding to -16. So I think -20 and 4 will do those jobs for me. So I will split my middle term up here into +4r and -20r. Factorise in pairs. So I get a nice little bit of quadratic practice while I'm at it. So remember, I'm solving for r here. My common ratio. Let's think about the results. 5/4 or -1/4. Remember, we assumed that from the information we were given, it's a convergent sum. So it has to be between -1 and 1. So It can't be r equals 5 quarters because it would be divergent. At -1/4 though, I've got a convergent sum. So that's my value of r. Okay, cheers.